Here I've simply summarized the solution to the second order differential equation for the phasor voltage that we've already stated, and I've gone ahead and written the solution to the similar analysis had we carried it out for the current phasor. Second derivative of the current phasor minus gamma squared I of, or the phasor current I bar of z is equal to 0. If we were to apply second order differential equation techniques, we would end up with this solution here. So we've got these two, what we call the traveling wave equations. One is the voltage traveling wave equation, and one is the current traveling wave equation. And what they do is they kind of describe what's happening to the voltage and current on a transmission line. So let's explain what each of the little parts of these equations mean. The first thing I want you to remember is that gamma squared was equal to r prime plus j omega L prime times g prime plus j omega C prime. That was from our KVL and KCL analysis earlier, and so what that says is gamma is equal to the square root of r prime plus j omega L prime times g prime plus j omega C prime. And if we were to carry out the multiplication underneath here and then take the square root of it, we would get some number that had a real portion associated with just the r prime and the g prime, and we would get some portion that had an imaginary because of the j's that are underneath that radical there. And it turns out that this is alpha plus j beta, where alpha is the attenuation constant that we showed in the traveling wave equation, and beta is the wave number that we showed in the traveling wave equation. So in general, the complex propagation constant gamma is equal to alpha plus j beta, and how you calculate their values is you just perform this math under here. You'll get a complex number. The real portion of that complex number is alpha. The imaginary portion of that complex number is beta. So just remember that. So now that you know those, well, what does that tell us about the voltage along the transmission line? Well, the voltage along the transmission line is going to be a cosine wave traveling from left to right. That's what this represents. This could be rewritten as e to the minus alpha plus j beta times z, which if we undo the phasor notation is just going to be e to the minus alpha z cosine of omega t minus beta z. So that's this portion. This portion here transfers into a little cosine wave with an attenuation constant in the front of it. V bar plus, it turns out, is equal to some magnitude. So that's just the peak amplitude, and it's a phasor number, so it's got a phase shift associated with it. And so if we were to combine those, this term here is just going to be V bar plus e to the j phi plus. Sorry, that's not what I meant to do. Excuse me. It's going to be magnitude of V bar plus times e to the minus alpha x cosine of omega t minus beta z plus phi plus. So this whole thing represents a cosine voltage wave traveling from left to right. And similarly, this portion here represents a cosine voltage wave traveling from right to left along the transmission line. So we've got voltage wave moving in that direction, voltage wave moving in that direction. Similarly, we've got a current wave moving from left to right and a current wave moving from right to left. So if we were to plot those, basically what the first half of either of those equations is saying is that we've got a waveform that's propagating from left to right. It's attenuating as it goes. It's got an initial amplitude there of magnitude of V bar plus. That's how tall it is. And it's getting smaller as it goes that way. The second half of that equation, if we were looking at the voltage, is this thing, and it's going to be a voltage waveform that gets smaller as it goes from left to right. The amplitude here at the output end of the transmission line is V bar minus, and it's moving from left to right. In both of those, the attenuation constant is described by this minus alpha x. Right? So what these equations are saying is that the total voltage at any point along the transmission line is just the sum of a left to right moving cosine wave plus a right to left moving cosine wave. And the total current along a transmission line at any point in space is equal to the sum of a left to right moving current wave plus a right to left moving current wave. And so that's the general solution to the transmission line equations there.